In the previous video, we talked about inverse functions, what it means, and then the properties. We did one computation problem, but that was rather simple case. Let's do a little bit more challenging problems, how to calculate inverse function. Now we have 3 problems here. First one is already done, and problem B is an important class of problem, and this kind of function is called linear fractional map, linear fractional function, because it's a fraction but both numerator and denominator are linear. Also it is called Möbius map, Möbius function, and that's the same Möbius who studied Möbius band or Möbius strip. And amazingly, the idea of Möbius strip is related to this function. It's complex function, but technique is pretty much the same. The reason I'm telling you this history as digression is because I want to emphasize that this is an important class of problem, and please remember the typical technique here. Now, how do I get it done? Switch x and y and solve for y. Okay, here we go. So the first step is to switch x and y. Y equals to g of x, 2x plus 3 over 3x minus 1. So switch x and y, we have x equals to 2y plus 3 over 3y minus 1. We are looking at a fraction, so it looks like I'd better increase the font a little bit. Okay, so we switched x and y. Now we have to solve for y, but that looks to be a little bit challenging because there are 2 y's. So that could be a bit of a problem, but out of desperation, I just got rid of the denominator. Well, okay, that may be an exaggeration, not out of desperation. If you have denominator, that's complicated, so killing off denominator by multiplying denominator to both sides of the equation is pretty typical thing for a rational equation. So it's not really outrageous, not really desperation. It's a typical step. But still, how will that help us? Consolidating these 2 y terms into 1 is not answered yet. In any case, we no longer have denominator, so it's simpler. Now break up the parentheses. Why do we do that? Well, that's simplification. So just distribute x around and let's break up the parentheses. So this is what we get. 3xy minus x is equal to 2y plus 3. So we just broke up the parentheses by distributing x. Does it help? We still have 2 y terms here. Well, here is a key step. Get all the y terms in one side, move everything else to the other side. So this 3xy is in right place. Okay, let's keep it there. This 2y is in wrong side, so let's move to the left hand side. This plus 3 is okay, but this minus x is in wrong side, so let's flip it over to the right hand side. If I do that, this is what I'm getting. 3xy minus 2y, because this 2y is flipped over to the other side, so I have to change the sign. And this minus x is flipped over to the other side, so we have positive x. Now I think everybody can see what's to come and why we did this thing. We have 2 y terms here, here and there. But if I factor that y out, now we only have one y expression here. I just factor y out, and y times 3x minus 2, and right hand side is x plus 3. Now it's pretty clear. Divide away this 3x minus 2, then I'm going to get y equals to this fraction, x plus 3 over 3x minus 2. And that is the inverse function. You can stop here, but I just decided to go one further and get this f inverse notation. F inverse is x plus 3 over 3x minus 1. 3x minus 2, excuse me. One more thing, one more comment. The domain of the original function was x was not equals to 1/3, because that's when the denominator becomes 0. The domain of this inverse function will be everything except x equals to 2/3, because that's when the denominator becomes 0. But then again, that happens to be the range of the original function actually. By the way, why am I using f inverse here? The original problem was given as g, so I should have used g. So domain of g is all real numbers except 1/3, which will make the denominator 0. And the domain of the inverse function is all real numbers except 2/3. That's when this denominator becomes 0. And, well, is the range of the original function equal to this domain of the inverse function? Or is the range of the inverse function equals to this domain of the original function? The answers to both questions turn out to be yes, but I'm going to leave those to the students. Instead, let me just show you the plot. So blue is the original g and red is the inverse function. Please note that we have a symmetry with respect to the diagonal y equals to x. Okay. Before moving on to the next problem, let me mention the key steps again. Switching x and y, go ahead and do that. And killing off the denominator and breaking off the parentheses are just simplification steps. The key step is right over here, getting all the y terms on one side, moving everything else to the other side. And in order to do, the reason we are doing this is to do the next one. We want to factor y out. So you have to foresee what you're doing in step 4 all the way from step 1. As a matter of fact, from here you have to foresee what you're going to do later. Now once this is done, you can divide away 3x minus 2, then you have an answer. If these numbers are different, you can do something similar. This one works for any kind of linear fractional map or any kind of Möbius map. Okay, let's move on to the next problem. H of x is given as 2x squared plus 6x minus 1, and then actually we have this domain here, x is greater than or equal to negative 3/2. That's when this function is 1 to 1. So this is a quadratic function, isn't it? It's a parabola. So if we take just one part, or this right hand side half of the parabola, then that's going to be 1 to 1 function. But then again, in a lot of situations, actually this may not be given at all. Excuse me. The problem may ask you to find out a domain in which this function is 1 to 1, withholding this information, x is greater than or equal to negative 3/2, and ask you to find out, and then find out the inverse function, and then find out the domain of the inverse function, and so on and so forth. So how do we find it out? Well, this problem explicitly gave you x is greater than or equal to 3/2, but let's pretend this part is not there, and let's find out. How do you do that? You have to express this h of x into the standard form. Standard form I mean by the vertex form. Here it is. Factor 2 out of first two terms, and then complete square. This 3 should be 2 times a certain number, so 2 times 3/2, and then you have to add 3/2 squared, 9/4 here, to make all the way from here to there as a complete square. Because I added 9/4, I have to subtract it so that I don't change anything. And this minus 9/4 will have to go outside this parenthesis, which I kind of screwed up here as a matter of, oh no, I didn't make mistake here. It can come out of this parenthesis, when you do that, you have to multiply by 2. So we have 9/2 there. Now this part, this parenthesis part, is a complete square. X plus 3/2 squared. And then consolidating these two, combining these two, we have negative 11/2. And then you can see what is the vertex. The vertex is negative 3/2 comma negative 11 over 2. And the right hand side will be coming from this vertex form. When x is greater than or equal to negative 3/2, then we have the right hand side of this parabola. So we have one-to-one function there. And also we can see the range of this quadratic function is, well, greater than or equal to negative 1/2, negative 11/2, excuse me. So that's the range, so that's going to be the domain of the inverse function. Okay, now that we switched an x and y and then got this negative 3/2 and then got this complete square form, let's switch x and y and solve for y. Okay, we switched x and y. And then let's solve for y. So let's move this negative 11 over 2 to the other side, as we see over here. And then we want this complete square, so let's move this 2 away. So divide by 2. Now right hand side is just complete square, so take the square root of both sides, and then the right hand side will not be a square anymore, because I just took square root to kill off this square. So y plus 3/2 is equal to that square root. Finally, moving the 3/2 to the other side, we are going to get y equals to square root of x plus 11/2 over 2 minus 3/2, and that is my inverse function. And when is this inverse function valid? What's the domain? I can see it. Number 1, from the inside of the square root is greater than or equal to 0. From that, I can see x is greater than or equal to negative 11/2. Or I can see it from the original manipulation here to complete the square. The range is, well, the square part is always greater than or equal to 0, so y is always greater than or equal to negative 11/2. And again, they match each other. They match. So the domain of the original function is when x is greater than or equal to negative 3/2. And the domain of the inverse function is when x is greater than or equal to negative 11/2. That happens to be the range of the original function, and this will be the range of the inverse function. Well, let me pause this video and then type in some mathematical command so that I can show you the graph. Just give me a moment. Okay, welcome back. Here is the plot. The blue graph is the original function, y equals to 2x squared plus 6x minus 1, and it's a part of parabola. Only the right hand side half of the parabola. Actually, after hitting the vertex, the left hand side parabola part should be there, but we threw those away. If we do not, then we are not going to get inverse function, because the blue graph, the original function, will not be one-to-one any longer. The red graph is the graph of inverse function. Square root of x plus 11/2 over 2 minus 3/2, and that's when x is greater than or equal to negative 11 over 2. And that's red graph is that a square root function. It's a part of the parabola. As you can see, we have desired symmetry with respect to the diagonal y equals to x, which is represented as a green dotted line here.